Okay, hello everyone. So this is the second installment in our CU Prime Talks series this year. So CU Prime is an organization here at CU, obviously, that aims to foster an inclusive community in the physics department. So this talk series features speakers with a wide variety of backgrounds and experiences, and have them give talks on their physics-related research. So today we're going to have Tyler McMaken.
Great. Yeah, just a quick update. If you see that QR code there, if you are in the room with me today, be sure to sign in on the laptops in the back, or you can just scan that QR code if you have not already. So that lets us know how much pizza we should be getting. Also, eat pizza, there's plenty left, but also make sure that you are wearing your masks if you're not actively eating pizza. So does that sound good for everybody? All right, wonderful. Yes, and we're also streaming live on YouTube. So feel free at any point to interrupt me if you have any questions. We'll have about 10 or 15 minutes at the end for questions when we get to that point. But also, if you are on the live chat on YouTube, you can ask questions there as well. We should be monitoring that. So like Hope said, I'm Tyler McMaken. I'm a grad student here at CU, and I study black holes. So I've titled my talk, Just How Black Are Black Holes? And I'll give you just a spoiler. The answer is they're very black. So there will be some subtleties with that answer. As we explore what's going on, we'll see particularly two things that are happening: gravitational red shift and Hawking radiation, that both will complicate that answer. But the main way that we'll go explore this is using a ray tracing code that my advisor had developed a while back that I'm starting to get access to. So it'll be a fun time. We'll get to see black holes and do some cool stuff. So as a starting point, usually in these CU Prime talks, we like to focus on the speakers and contextualize their research and kind of personalize it. And so I'm going to tell you a little bit about my history and what led me to want to study black holes in the first place. So I started out, I grew up in Ohio, in Columbus, Ohio. On a map, here it is right here. So I really enjoy this map. This is a map that tells you what the most common autocorrect answer is when people type in "why is Ohio," for example, so. So for Ohio, people apparently type in "why is Ohio so important?" I think the top two other answers for that were flat and powerful. So make of that what you will. Ohio's a pretty cool place, but also there's some cool other states you can see there. We're in Colorado. Why is Colorado so fit? I don't know. So in Ohio, I grew up there my whole life. I did my undergrad also in Cleveland, Ohio, at Case Western Reserve University. So Case is a great biomedical school, and they also have a lot of snow and really great weather. And by great weather, I mean pretty terrible weather. So it's cloudy most of the year round. There's a lot of snow. Here's what my graduation looked like. So lots of rain. I guess I'm in the way. But yeah, you can see that. So what did I do at Case Western? So I didn't just major in physics. I also majored in music. So I play piano. Does anybody here have an interest or a passion in music? Wow, so more than half the room. Yes, music is great. So I play piano. I also play organ and harpsichord, so all of the keyboard type instruments. And that was really a good avenue for me to be able to, I guess, to pursue a passion that was not physics. So it helped me to relax whenever I was working on a tough physics homework assignment. I just play piano and operate the other half of my brain. I also did minors in astronomy and mathematics. Those were both side interests of mine, I guess. And when I started to end my undergraduate career, I started to think about what I wanted to do in my future. And grad school came to mind. And I realized that I hadn't really done any research at Case Western. So I was a first generation student, so I didn't really know that to get into grad school, it's really important to start doing research early. And so I did not really get started on that at Case Western until senior year, but I also had some summer opportunities where I did research before that. So I did these things called REUs. Does anybody know what that stands for? Yeah, I'm back. Yeah, research experience for undergraduates. So these are summer-long, basically internships. They're things you apply for. And you basically get to spend a whole summer doing research, studying under some professor at some university. It could be the same university that you're at. So CU Boulder has a number of RUs, or it could be somewhere across the country, or even across in another country. So I did 2 of these. I did one at University of Notre Dame, and there I had a project on experimental nuclear physics. And that was fun. That was where I got my first poster presentation at a conference. And then I also did an RU at the National Solar Observatory right here in Boulder. And so there I was studying an active region on the sun that appeared in 2014 and really messed up the solar cycle. So it was cool research that I was engaged in there. And that led to my first published paper. And so both of these opportunities really helped me to get a footing in grad schools as I was applying. And as it turned out, the only 2 grad schools that accepted me after I applied to a whole bunch were these 2, University of Notre Dame and CU Boulder. So I ended up coming here to CU and I started doing grad student stuff. So what is grad student stuff, you may ask? Well, at first, a lot of it is basically the same as what you do in undergrad. So I took classes, I did things like that, but I also started to look for research. So I went around, I eventually had found an advisor after a semester or 2. And at that point, I started doing research, what I'm currently doing, which is theoretical astrophysics, looking at what happens inside black holes. But that wasn't all I did. So I also played music, just like I did in undergrad. It wasn't for any formal thing, but for example, here's a picture of me playing harpsichord with an ensemble over in the music department. This was pre-pandemic, but since then I've been able to do a lot more playing organ and piano at my church and other opportunities like that. So I played music. I also enjoyed the outdoors. So this picture, which should come up, is I enjoy hiking and trail running and all those sorts of things. And so my first year or 2 in grad school were pretty good. I was exploring all of Colorado. It was wonderful. It was a lot different than flat Ohio. And then the earth got sick and COVID-19 happened. And so this was a big change for everyone. And I'm sure if you go to other of these CU Prime talks throughout the rest of the semester, then hopefully you'll get to hear about how different grad students have had to handle global lockdown for a year. And so for me in particular, I actually was rather fortunate. So I am a theorist, and that means many things. In particular, I'm not an experimentalist, so I don't have to go to a lab. I don't have to build lasers or worry about cryostats breaking or plumbing or anything like that. Instead, I can do all of my work from my laptop in the safety of my home. And so it was rather nice that during the whole lockdown, I could basically keep doing everything that I was doing. And it was basically not much of a change, but it was still quite a bit of a change for me. Because as a theorist, the downside of that is that you don't have a lot of funding. So it's a lot harder to get funding when you're doing theoretical work instead of experimental work. And so in particular, that means that I have to teach. And that's primarily how I get my funding, as a TA. So this continued through the pandemic. I still had to teach. So here's a picture of me teaching last spring, I believe, in the lecture hall, which at the time was completely empty except for me and my complicated technological setup. Everybody else was on Zoom. But that was a fun time. And that took up a lot of my time at the time, but it didn't take up all of my time. So you might ask, what does a theorist do in their day-to-day life? And the answer, at least for me, is that every single day looks different. So some days I'm prepping for teaching. Some days I'm teaching. Sometimes I'm reading papers or reading textbooks, or maybe trying to write an academic paper. Or sometimes I'm just struggling with mathematical code. So I use a code called Mathematica. You can see there on the left side of that screen. This is a screenshot, I believe, from last week when I was preparing this presentation. So Mathematica is just a computational code, which is a beefed up version of Wolfram Alpha, if you've used that website before. And so, yeah, the other thing you might notice about this screenshot is that I have a lot of tabs. I am a tab hoarder. And most of these, I believe, are just papers that I've been referencing or I've yet to read, wanting to read. Anybody else really like tabs? It's a pretty polarizing thing, I know. Yeah. So that's great. So I do things like that. I also sometimes do scratch work. So here's what the whiteboard in my office looks like right now. So I draw things out to help me visualize what's happening in a certain model, or maybe I'm trying to figure out how an equation works. So we can get more into the details of what specifically I do and what you're seeing here on the screen right now. But we should probably start somewhere a bit simpler and talk about black holes. That's what we're all here for. So we are here to talk about this, a black hole. This was a picture that was taken back in 2017. It was really, the publication came out a few years after that. And there are actually several faculty members here at CU who work on black holes, and even specifically this picture. So Jason Dexter is a faculty member in the APS department who studies, or who is a part of the team that created this picture and who ended up getting the breakthrough prize as a result of that. And the thing is, most of the faculty here at CU who work on black holes study the orangish ring around here. So this is a top-down view of a black hole. And what we're seeing here is a whole bunch of debris and clouds of gas, which are swirling around as the black hole tries to swallow it up. This is called the accretion disk. And there's a lot of modeling and simulations and computations that go along with that. But that is actually not what I study. What I study is not pictured here, and it probably can't ever be pictured. So I study what happens inside black holes. So you'll see in a second, hopefully, why I say we can't picture these things at all. But the work of a theoretical physicist is nice because we aren't bogged down by experiment or anything like that. So maybe observationalists or experimentalists will have to worry about, oh, we don't really have the resolution on this telescope to see these things, or we have to get above the atmosphere to get rid of this noise. But for a theorist, if we have a model, then we can go where no human has tread before and where no human will ever dare to tread. And so for me, that means that I can use models to visualize what happens inside black holes. So our story of black holes starts about 100 years ago in the year 1915. And this is when a guy named Albert Einstein came up with the theory of general relativity. So this is a theory of gravity. There's a picture of Einstein right here. He, as it turns out, was an avid violinist. He also played piano. He said that was a big part of his life. If you're curious, just thought I'd throw that out there. And what he was wondering about, though, was how he could create a theory of gravity that improved upon Newton's theory of gravity, which had been in place for a few centuries before that. But there are some discrepancies. And so Einstein's general idea was, what if we were to treat space and time as a single unified geometrical object? And this thing he called space-time. And so the picture that we generally see with the space-time is something like what you'll see on here on the left, which is that space-time is like a grid or a rubber sheet of sorts. And so if you have some massive gravitating body like the sun, it's going to pull down on that sheet and it's going to create some curves. And so any object which is moving in that space-time is simply going to follow along those curves. And that applies also to light. So if you have a light ray, it's going to travel just along the path of least resistance. And this is not predicted by Newton's theory of gravity. So Newton would say light does not have any mass, it doesn't have any weight, and so it is not attracted by gravity, it's just going to travel in a straight line. But Einstein said, well, what if light, the space-time itself, is what gravity actually is, and anything, even light which is moving through it, can get curved by it. And so it turned out just a few years later, they tested this out. They were looking at stars which were just behind the sun, just like is pictured here. And they found out that it was true. The light from these stars was actually bending around the sun when it normally should be obscured, we were actually able to see a star. And so this gave credence to his theory. It was wonderful. I, in particular, don't like this picture of grids too much for several reasons, mainly because it doesn't really give any information about time. So all we have here is a two-dimensional grid. And so we're immediately losing. So in reality, space is 3 dimensions. We have length, width, and height. And we also have 1 dimension of time. So that's 4 dimensions in total. Now it's kind of hard to visualize 4 dimensions. I don't know if you guys have ever tried to do that, but it's pretty terrible to imagine. But I think the best that I can do is something like this. So we have, behold, the gift of the ocean has presented a pizza. So why am I showing you this? Well, what if we imagine that the water is the space-time? So we have this 3-dimensional thing now. It can carry things within it, and it's moving in time. So now we have all 4 dimensions all together here. And we see that usually, if we're just dealing with normal everyday things, space-time is what we call flat. And that means water is just completely still. We move around normally, but we can do things like add waves. These would be gravitational waves, or we can have the water flowing in a certain direction. And anything which exists within that space-time, like say our pizza, is just going to go along with the flow of that space-time. And it might feel some force as it passes over a wave. It would call that gravity. But if we're looking at this from the outside, we say, oh, this is just space-time moving in this specific way. So equipped with this picture, we can start to think about what black holes are. And specifically, I'd like to propose the definition that a black hole is a place where space-time is flowing faster than the speed of light. So usually when I say this, people are confused for 2 reasons. The first is the statement that space-time is falling. And this hopefully is something that is not confusing anymore if you think about it in terms of this water picture. So space-time can flow around, we just get carried along with it. But the other thing is that space-time is falling faster than light. So there is a theoretical speed limit in the universe, and that speed limit is the speed of light. So nothing can travel faster than light, because in order to do so would require an infinite amount of energy or a negative mass or something weird like that. And so the only way that we can get around that speed limit is by saying, what if the underlying space is moving faster than light? So we ourselves could be sitting at rest in this space, and we would just be carried along. So we would think we're at rest, but with respect to someone who's really far away, they're going to see us and they're going to say, oh, they're moving faster than light. So right away, you should say, well, wait a minute, maybe that is kind of weird, fantastical. Maybe it works out mathematically, but I'm not so sure I believe that. But this was the solution that people came up with just months after Einstein published his theory of general relativity. This guy named Karl Schwarzschild came along, and he basically discovered this first model of black holes, what we now call a Schwarzschild black hole. And this is the simplest model, and this is the model that I'm going to be presenting throughout the rest of this talk. The basic idea is that we have a spherically symmetric spacetime where everything is falling into the center. So that's it, that's all that we require here. And as the spacetime gets closer and closer to the center, the faster it falls. So here we have a little bird which is falling into a drain. That's pretty cool. Maybe there's a better way to explain this. I have an animation here, which is the same picture, except for now we have arrows which replace our water before. And so in both cases, all you can imagine is you are sitting in the space-time. If you are at rest, you're just going to be carried along by these arrows or by the water. And eventually, you reach a special point. So the main point of this black hole that's worth mentioning is the horizon. And the horizon is the location where space-time starts to travel faster than light. And so if you're just sitting on one of these arrows, you can be outside the black hole. Everything's fine, you can go in any direction you want. But once you get within that horizon, suddenly you are going faster than the speed of light with respect to someone off at infinity. And so what that means is no matter how hard you paddle to try to get out of this black hole, if you're in a canoe, for example, you can pretend you're going outwards and you will think you are going outwards. But in reality, once you are within the horizon, you have to inevitably go to the singularity at the center. Yeah, you have questions? What was that? Oh, I see what you're saying. So the question was about warp drives. So trying to break the speed limit of light by having some vacuum where you create a special solution. And the answer is that is exactly it's very similar to what's going on here. So there is this theoretical possibility that we can have a space-time where the space is traveling faster than the speed of light. And we're just sitting there at rest in our little, what we would call a warp drive. And we can move however far we want, however fast we want. So yeah, that is a theoretical thing. It turns out, I believe there's some problems when you try to add quantum mechanics to that the second that it starts to go faster than light, there's this weird horizon thing that happens. We might have time to talk about that more at the end, but good question. Right, so with this picture, we have a black hole and we have space falling inward faster than light. Oh, did you have a follow-up? Oh no, you're blocking the sun. Okay, yeah. So at the time, as I said, Schwarzschild didn't really fully understand what was going on with the solution. But nowadays we have computers and we can actually do a lot more to understand what's going on. So there's this thing called ray tracing, if you guys have ever heard of it. And it's a pretty simple concept. It happens all the time in just about any video game that you play. The idea is that if you are an observer, a viewer of a scene, and you track every single ray of light which hits your eyeballs, and you take them, you trace them backwards, then eventually you'll find out where those light rays originated from. And you can place them at some point on a background, and then you can reconstruct what the scene looks like from your perspective. So this is a pretty simple task when it comes to video games. And the reason for that is because you can just assume that light travels in straight lines. In this case, though, light does not travel in straight lines. And so in this case, you have to use these equations of general relativity, specifically the equations of this model of the Schwarzschild black hole that we have. And it turns out that these are equations that involve integrals that have no analytic solution. So the only way to integrate these things is by sticking them into a computer or by looking up some integral table in a textbook from 100 years ago or something like that. So it's a lot of work, but as it turns out, we now have software that can do that in real time. That's the software that I'm going to be showing you today. As a quick primer to that, on the bottom left of the screen of this software, there's going to be a map. And this map is basically the same picture as what you see in the middle here. So we have in particular, the red circle is the horizon. And so this is the location where the black hole starts, basically. And then we have a dot that shows your location. And then we have a path behind that, which shows where you have been flying through the scene. So your trajectory. And that's all that you need to know with this map. So there are colors there as well that tell you about whether or not the orbit is stable or things like that. But the important thing that you'll need to remember is that the red circle is the horizon. Okay, so are there any questions so far, or should I just go to the simulations? Oh yeah, you have a question? Okay, good question. So the question was, if space-time is falling faster than light, is there infinite energy? I would say no. And it's not really clear what mechanism causes space-time to fall faster than light, but there is a fundamental difference between space-time and things that exist in that space-time. And so we can come up with whatever arbitrary rules we want for how the space moves around. But once you put an object in it that has mass, then that thing has to obey this speed limit. So interesting question. Yeah, you have a follow-up?
In the water analogy that you used, the water is
flowing to something. Whereas in here, my understanding is it's just infinite point density. As it accumulates mass and everything, does that get bigger? Or like, I'm trying to understand flowing. It flows
Right,
into a
yeah.
singular point, and that's hard to see.
Yeah, it's a good question. So he's asking about how we're flowing to the single point. What is happening there? And so there's not actually any. So I didn't talk much about the singularity yet. So this is a region of infinite density. So a black hole forms from the collapse of a star, and it all gets crushed down to a single region called the singularity, where all the matter resides. So when we say space-time is flowing, it really is flowing towards some sink. You can imagine it pours down a drain. And wherever there's a drain, that means that there is mass or energy. Einstein says those things are one and the same. And so basically, we can imagine that any mass is going to create a sink for the space-time to flow into. This includes all of you. So you are all massive, gravitationally attractive bodies. And so we are all attracted to each other. And space-time is flowing into us. It's a weird concept, I know. Yeah? Oh, what is the relationship between mass and space-time? Sorry? Okay, the definitive relationship. So the relationship between the two is given by what are called Einstein's field equations. And this is the basis of general relativity, is we say that the curvature of space-time is related to the stress energy is what we call it. So this is the mass energy content of the space-time. And there are these specific equations which tell us how that relates to the curvature. So yes, there is a well-defined model to understand this. All right, so let's see if I can get this running up here. Oh no. Okay, there we go. So can we all see this? All right, wonderful. So what we are seeing here is the Milky Way. Have you guys ever seen the Milky Way? Okay, hopefully, I would wish that every hand in the room were raised. If you have not, go out into the mountains sometime where it's really dark. But we can see that there is this band of bright stars around us. And this is the stars from our galaxy. We are in a disk. So if the galaxy were just a complete sphere, then we wouldn't really see any Milky Way per se. But because the galaxy is a disk, then we see this concentration of stars right there. At the center is a black hole. We're not going to talk much about that one. So what we're going to imagine is that we are on Earth, because we are on Earth, and we take the sun and we crush it down. So the sun is still the same mass, but now we're going to imagine that it's crushed down to the size of a black hole. So if we were to do that, let me ask you guys, how big do you think the sun would be, our new black hole? So the sun is 2 × 10⁻30 kilograms. So it's really massive. So a black hole is going to be smaller than the sun, but how much smaller? Any guesses? Okay, I saw your hand first. The size of Boulder. Do you guess any others? Size of a proton, all right? We couldn't see it. So like smaller than a proton? Or well, I guess those aren't mutually exclusive. Yeah? Size of a basketball. What was that? An apple? Anybody from over here have any guesses? Yeah. Size of Texas. Okay, that's a good range. As it turns out, it is pretty close to the size of Boulder. So in particular, I guess it would be about the size of Green Mountain. So it's a radius of 3 kilometers, I believe, or thereabouts. And so what you can imagine is this giant mass of the sun is all being crushed down, and that's the radius of the event horizon. And so the mass itself is going to be even smaller than that. As it turns out, this actually can't happen. So the sun is too small to form a black hole. So the smallest black holes that we see are usually about 6 times the mass of the sun or larger. The black hole at the center of the galaxy is 4 million times the mass of the sun. So they have quite a large range of masses here. So here we are staring straight at the black hole here. You can barely see it on the screen. It's a tiny black dot. And I believe this is artificially blown up, so we shouldn't actually be able to see it here on Earth from this far away. But what we can do is get closer, I believe. Okay, so now we are closer. Nothing has changed. So in particular, I think now we are the closest that we have ever approached to the sun. So this is where the Parker Solar Probe has gone within a few solar radii. And we see that still there's nothing. So if the sun were there, we would be right at the doorstep of touching the edge of the sun. But now there's just a tiny little black hole. Let's go even closer. So now we are going to go a 1 Earth radius away from the sun, or from this black hole. Yes, so now we start to see something interesting. Let me zoom in here. We have binoculars apparently. And what we can see is that it's starting to distort the space-time around it in just the subtlest way. And in particular, we can see that some things are repeated. Let's see if I can try. So there's a star here on the left side, and that star is actually repeated where my cursor is going right here. So that is the same thing. So as it turns out, that star is behind the black hole, and the light from the star is bending 2 different ways, one to the left and one on the right side. And they're both reaching us so that we have 2 copies of the star. So a black hole is a mirror or a lens of some sort. It bends around light in weird ways. We want to get closer though, don't we? So we're going to slowly drive into this black hole. We're not going to go all the way. I guess I should pull up here this thing. I promised that I would have this. All right, so now we are about 100 miles out from our black hole. So I'm going to start orbiting it. And I'm going to speed up time so that we can start to see the orbit. Is this going to happen? Aha, okay. So now we can see on the bottom left the trajectory that we're going in. So we're going in a circular orbit around this black hole. And we see that it's distorting the space-time around it. And it's kind of hard to see here on the projector because everything is black around it at this point. But once we go around again so we can see the Milky Way, then we'll get quite a nice picture here. Okay, so I think we should get even closer, shouldn't we?
Yeah.
Oh, not that close. Okay. Let's see. So, ooh, this is interesting. This is a new experience for me. Okay, so something broke. And now everything is black instead of white. All right, what I'm going to do is restart the program. How about that? When in doubt, this is what we can do. So it takes about 15 seconds to load up. So my apologies for that. But my computer is very slow. But that is okay. So, all right, we're back at our black hole. I think there are some things I had to configure first. And we are going to take the radius of the observer to be, oh, I don't know, 300. What does that do? Oh, perfect. Okay. So now we are pretty close to the black hole. What I wanted to show, if I can get this up here. Let's start orbiting here. We're pretty close, but one other thing that I can do is I can launch objects. Ooh. So we can see this thing is going to fly off above us and we'll eventually see it out of sight. What if I were to launch something into the black hole? We could ask what that does. Well, let me just throw a few boxes here. They're kind of slow, I guess. Okay, so I've thrown 4 boxes. We're going to follow them along here and see what happens to them. Why are the boxes twisting? That is an excellent question. So one of the reasons is I was rotating them as I threw them out. And so they're twisting because of that. But there are also some weird curvy things going on. And this is because the time that it takes the light from one end, from one corner of the box, versus the time it takes light from the front corner to reach me is different. And the curvature of the space-time in those two regions are different. And the speed of the box from each corner is different. And so that's a special relativistic effect that I won't spend too much more time talking about, but it's a cool effect. Okay, so it looks like 3 of the boxes made it down. Did you guys see what happened to them? They just kind of disappeared, didn't they? So it goes down there, it kind of changed color a little bit, and then eventually it disappeared. But the weird thing is that it didn't actually, we're not actually seeing it fall into the black hole. So we know this because if we look at the map right here, we can track where they are from our perspective. And we see that all of them are sitting at the horizon. So this is one magical thing we can do as a theorist is we can, even if we can't see these things, one thing I can do is put on radio vision. So I have goggles that can turn on radio. So light, optical light is part of an electromagnetic spectrum. It's not just visible light that we have in front of us. Light can also be X-rays, gamma rays. On the low end of the spectrum, though, is infrared and microwaves and radio waves. So if we were to look at that end of the spectrum, here's what we would see. Okay, so this is a very different view that we're seeing now. So the Milky Way, we can see above us as this bright ring. And there are these wisps of gas and clouds which are going out from the Milky Way that we can see. I don't want to talk too much about why that's happening. The main thing I want to see, though, is that we have our boxes, which we can just barely see here on the horizon. It's kind of hard to see here on the screen. I can try to turn up the brightness a little bit. So we can see that the boxes are just barely there. They're kind of, oh, now it's going very fast. They're just kind of frozen there on the horizon. Yeah. So the question was, how does the study of dark matter affect the study of black holes? Yeah, good question. So I haven't really talked about dark matter at all, have I? And it turns out that you actually don't need dark matter to form black holes at all. So they work completely independently of each other. But we do know that dark matter acts gravitationally. And so a lot of people do study how dark matter, it's just another source of radiation you can imagine. So yeah, good question. So I guess what did I want to say about these boxes? So we still see them at the horizon, kind of frozen there. The reason for this is if you imagine light being emitted from these boxes, if they're close to us, the light just goes straight from the box to our eyes, no problem. But as we get closer and closer to the horizon, space starts to fall faster and faster. And when they're right above the horizon, any light which is emitted from the box is going to travel outwards, but it's swimming against the current. And so it's going to take a lot longer to reach us than it would otherwise. And so when we think about this light, as it approaches the horizon, it's going to take longer and longer to reach us, which means we will see the boxes slowing down. And also, once the box passes below the event horizon, we'll no longer see light from it, but we'll still see the light from when the box was just above the event horizon. So we'll still see that light until an infinite time in the future. And so essentially this light is, we're seeing this thing slow down. Did you have a question?
So is it like this space-time
Yeah, I think you can imagine it as a treadmill. That was the question, right?
Yeah.
Right, yeah, that is a good analogy. So if you are running on a treadmill, you're going very fast, but the treadmill, the space-time beneath you, is going at the same speed in the other direction. So in the same way, these light rays are going outward right at the horizon, but they're going to hang there for an infinite amount of time as they struggle to go outwards, but can't do anything. So one other thing that happens, you'll see everything is kind of red. This is an effect called gravitational red shift. And the basic idea is that the light is losing energy. And the only way that it knows how, it can't lose energy. Usually when we lose energy, we just slow down. But light can't do that. It always has to travel at the speed of light. And so instead, it slows down its frequency, which means it changes color. And so it becomes more and more red. And eventually, it becomes so red that it's redder than we can see. We call this infrared. This is out of the visible range of the spectrum. And then it becomes even more red until it's now in radio. So essentially, these things which are falling into the black hole, which applies not only to the boxes I threw in, but to everything which has ever fallen into the black hole before. We see these clouds of debris all over there. In theory, the star which originally collapsed to form the black hole would also be visible here. But by the time we reach now, it's so redshifted and so dimmed and so slowed down that we basically don't see anything anymore. So black holes then are truly black if I return then to our normal view. Okay, so I have a discussion question for us now. I believe, yes. So what I'm going to do last in the simulation is figure out what happens when we go inside the event horizon. So we have yet to do that, but in principle, we can fall below this region that we see of everything that's frozen on that surface. So if we were to do that, I want you guys to turn to your neighbors and discuss for a few minutes, what might you see? What might you feel? How much time might pass? Will something special happen? What do you think will happen? So I'll give you guys a few minutes to discuss, and we'll come back together and we will see. All right, let's come back together here and talk about what you guys think you will see. So does anybody have any thoughts you want to share? What you discussed with your group? Yeah. I think you died. Did anybody agree with that? Yes, all right, this is good. Any other thoughts? I mean, it's not good that you're dying, but I just want to make that clear. Yeah? Okay, so spaghettification, that is an interesting term. Yes, so gravitational tidal forces will take over. That means that the force of gravity at your feet, if you're falling in feet first, are going to be a lot larger than the force of gravity at your head. And so you're going to get stretched out. So for this particular black hole that we're talking about, that will indeed happen. If you're falling into a supermassive black hole, like the one at the center of the galaxy, you will survive just fine if you're just outside of the event horizon. And you'll have at least a few hours while you're inside before you get spaghettified. So interestingly enough, the large black holes are the safest ones in that respect. Any other thoughts from any other groups? Yeah?
Yes, I studied about this. So when I learned that when we are approaching Earth, the time is actually gets slower. So if the black hole has a really large gravitational force, would the time just kind of stop for us?
Okay, that is a good thought. So what you're saying is that time might just stop. So if we were seeing these things that are getting thrown into the black hole and they just kind of freeze at the horizon, then something weird is going to happen with time, surely, right? All right, any other thoughts? Yeah. Right, okay, so Dement was thinking about pondering what you would see, and he said there were two options. One is that we would just see a whole bunch of rays streaming by us, and the other is that it'll all be black. Did someone over here have a, yeah?
When I'm but like from an outside perspective, like time and stuff, and you were able to look outside the black hole, time was either extremely fast or
Okay, so that was a comment on time as well, and saying that if you're falling in, time wouldn't stop for you because in our own frame of reference, and I agree with this, we experience time the way we experience time. So we have a clock, an internal clock. We can count a number of seconds, and there's not really much that can stop that unless, of course, we die. But from an outsider's perspective, they'll see us slow down. We've already seen that happen. The only question is, what will we see if we look back up? So let me just go to this since we don't have too much time left. All right, so we are back here at our black hole orbiting at a safe distance, but no longer will we orbit at a safe distance. So let me give us a bit of a kick, an acceleration so that we can start to travel inward. So now you can start to see on the map that we are diving in, and eventually we're going to cross the horizon. So here we go. And let me pause it right here. So we are just above the horizon at this point. So we can look straight up into the sky. It's a little red shifted as it turns out, but that's not too important. Everything else seems pretty normal. Now let's go. Okay, so we have gone below the horizon right now. We see that not much changed. So the Milky Way did a weird little twist thing. That's nothing really that special though. Everything else is pretty normal. So we still see a black hole shadow below us, and we still see the sky above us, and everything is basically happening normal. And this is what we should expect. So all of the light which is falling in above us is going to reach us. And so we still see everything above us, but everything below us is still this really red shifted stuff from the black hole shadow. And we haven't caught up to that yet. We never will catch up to that unless something weird happens that we don't know about of a quantum nature of singularity. But everything so far is still normal. Should we go all the way in? Looks like I've twisted myself up here. There we go. Okay. Let's continue all the way to the center. Okay, and something weird happened. The code broke because we reached a singularity. But fortunately, we have code and we can just go backwards in time. So I've done that here. Now we can see what it looks like just before we reach the singularity. So if I look around here, we see that the black hole has formed this basically infinite plane in front of us, below us. And above us, the sky is still redshifted, we can see. And yeah, we have this horizon of brightly blue shifted things right across us in all directions. So this is the singularity. It is not a single point. It is a surface. It is an infinite plane below us. And this is the black hole shadow. So everything that we see, all of our boxes are still going to be just below us. All of the collapsing star from what originally formed the black hole, it's still going to appear below us. But there it is. Okay, so, right, I wanted to comment on the time as well. So time behaved normally for us. And if we look back up, we would not see the infinite future, unfortunately. We perhaps could if we would have struggled and tried to stay in the black hole as long as possible. But since we just dived right in, time just went on normally for us. And we just see things continue to pass by, maybe a little bit sped up in time, but not too much. All right, and that is, I believe, about it. So I had a few extra things here about Hawking radiation. I'll just briefly mention this. So this is closer to what I specifically do in my field. So Stephen Hawking was a guy 50 years ago who came up with a way to merge general relativity, which is a theory that describes gravity and things on large scales, with quantum field theory, which is a theory that describes really tiny scales. So if we take a quantum mechanics class, we learn about all of these weird things with Schrodinger's cat, with particles that behave as waves, with double slit experiments. all of these things combine together into what's called quantum field theory. And it predicts that particles will pop in and out of existence, that you have particles and antiparticles, which will form as they borrow energy out of this quantum field, and then they'll annihilate and return that energy to the field. So this is apparently happening all the time. And the problem is when you try to mix these two theories together, you run into a lot of problems. You run into a lot of infinities in your calculation that don't get resolved in the normal way that they usually do in quantum field theory. And so finally, Stephen Hawking was able to do something pretty simple, first step towards mixing these two theories. And his prediction was that you would have radiation from black holes. And so the thing that you can imagine is that a particle and an antiparticle can pop into existence. And if they do that at just the right spot, so that one of them is outside of the horizon of a black hole, one of them is inside the horizon, then the one inside the horizon will fall in. It can never reunite with its partner. And then the one outside will become real and it will escape off to infinity and become radiation. So usually in these CU prime talks, we encourage speakers not to include any formulas or complicated plots because they usually just take away from what we're trying to say. In this case, I had to include this equation because I think it's the most beautiful equation in all of physics. So let me explain the reason why. This is the temperature of Hawking radiation. And we see there's basically a whole bunch of constants. And all of these constants are telling us very specific things. So we see H at the top, that is Planck's constant. And this tells us that quantum mechanics is involved. So H is the conversion between particle-like properties and wave-like properties. And so Hawking radiation could be perceived as a particle or a wave, depending on how you interpret it. We also have C, that's the speed of light. This tells us that special relativity is involved, or if you generalize that, general relativity is what we've been focusing on more here. On the bottom here, 16, that's not too important. Pi, though, is really important. So whenever you see pi in an equation, that tells you that there's some geometrical interpretation where you can imagine a circle that has a specific meaning in the problem. So in this specific case, we have a pi because we have a horizon, which is a sphere. And the area of the horizon, as it turns out, tells us about how much information the black hole contains, how many gigabytes of data is inside the black hole. There's also K sub B, that's Boltzmann's constant. This tells us that thermodynamics is involved. So that's the conversion between temperature and energy. And we have big G, which is Newton's gravitational constant. That tells us that gravity is involved. And so in this one equation, and there's M, which is the mass of whatever object you have. This one equation, though, contains all of these physical theories, which are all mushed together into a single thing, which maybe is not exactly ideally true, but it does get us pretty close to what we think should be the case. So let me just skip to the end here. So if I plug in all of these numbers, just an order of magnitude estimate here, for the black hole at the center of our galaxy, Sagittarius A star, we end up with a number 10 to the minus 14 degrees Kelvin. This is an extremely small number. So 0 degrees Kelvin is absolute zero. Room temperature is about 300, and freezing temperatures is 270 Kelvin. And so this is colder than anything that people have ever made. I believe the talk in 2 weeks that we have here is from someone who deals with cryostat at millikelvin temperatures, which is like cutting edge, really cold stuff. This is much colder than that. And so if we think about Hawking radiation, we imagine the black holes do radiate energy if we add the effects of quantum mechanics, but with the caveat that this energy is so small that we have never any hope of being able to detect it. And in fact, it's smaller than the cosmic microwave background. And so actually, this black hole is gaining more energy than it's emitting. Yeah, you have a question?
Yeah. So this isn't a
Oh, yes, good question. So you're asking, this doesn't have to do with the temperature right near the black hole. This is the temperature at infinity. Yes, so this calculation is specifically the temperature of radiation, assuming that you start out in infinite time in the past, infinitely far away from the black hole, and you end up in infinite time in the future, infinitely far away from the black hole. But you can, in principle, calculate the amount of radiation closer to it, and it ends up being about the same order of magnitude here. Okay, that's actually all that I have. So I'm going to end things here. And before we have more questions, I just have 2 extra slides to present just as announcements. So CU Prime has a mentorship program that's great. And right now we're just starting it up. And so if you are interested in being a mentor or a mentee, then be sure to visit our website, cuprime.org/mentorship. And you can sign up. There's a form that we'd like you to fill out. And yeah, being a mentor is a really great opportunity. I'm sure a lot of people in this room have done that themselves. And so I hope you guys will start to do that. And finally, if you want to give a talk yourself, you can also do that on a form online. But for all of you here in the room or watching online, feel free to fill out this quick survey to give feedback on how this specific talk went. So there's a QR code and there's also a link that you can do that. But otherwise, I'm glad I can be here. So thank you all for listening. And I can take any questions if anybody has. Yeah.
Yeah, suppose we have 2 black holes of same size. What would happen if they like collide?
Sorry, could you repeat that?
Suppose we have 2 black holes of same size, same magnitude of the gravitational force. What would happen if they both collide with each other?
Okay, good question. Imagine if you have 2 black holes, same size, and they collide. So this depends on several things. Depends on how much angular momentum they have with respect to each other. So whether they're just going head on or they're spinning. But in general, we would expect them to merge. So I guess the second that their event horizons touch, then you can imagine they become a single black hole. And for a little bit of time, it'll be kind of weird shaped. But the way that they work, what people have found is that black holes will radiate out all of the extra information about the different shape until it returns to basically a sphere again. And so that radiation will not be Hawking radiation, it'll actually be gravitational wave radiation. And this is something that we can detect. So yeah, this is what the LIGO collaboration has done, is detect the merging of black holes, and it's a really cool thing. Yeah.
So when the black hole, during the Hawking radiation, one particle enters the black hole and one is on the ground, what effect does that one particle have on that? However many times does that have direct effect on the black hole?
Right, so the question is, what happens to the Hawking partner which goes into the black hole? If I can summarize that properly.
Yeah.
That's a great question. That's of particular interest for what I study, since I study black hole interiors. So these particles are negative mass. So you can imagine the one of positive mass is the one that escapes to infinity. So the one with negative mass will then reach the singularity at the center, and it will basically become part of the black hole. So what that means is the black hole is going to lose mass if the maths work out all that way. And so eventually the black hole will be nothing. So it'll just have no mass. This won't happen for billions of years though. So within the lifetime of the universe, even a black hole the size of the sun would not have evaporated away to nothing. So it takes a really long time because we know it's really cold, but yeah, and way back there.
How would a black hole start
So did you say, how does a black hole suck in negative mass when forces of gravity prevent that?
Yeah.
Right, yeah, good question. Don't know if I have a really good way to answer that. One of the problems is that this picture of Hawking radiation, where you have a positive and negative mass particle, this is just one particular model we have of explaining it. And it doesn't really capture all of the true effects of Hawking radiation. So as it turns out, that it works out mathematically to give you the correct solution, but often it's not completely correct to think of it as a negative mass particle being sucked in. Perhaps it's better to think about a particle which is just able to tunnel out of the black hole. If you've heard of quantum tunneling, it would be similar to that. But there's also other ways to explain it. Yeah?
So my question is, does it have to be that insucted or
Okay, yeah. So does it have to be the negative mass particle that goes in? Does it have to be the positive one that goes out? Basically, yes. So this was a question that I struggled with a lot when I was first trying to understand Hawking radiation, was what exactly is the symmetry that's being broken that produces this? Isn't there going to be an equal number of particles and antiparticles that evaporate out? But the thing, it's a really weird effect that inside of a black hole, you're allowed to have negative energy and positive energy. And outside of a black hole, you're only allowed to have positive energy. And so that's kind of the asymmetry. And so what that means is that you can only have a negative energy particle on the inside. And that always ends up being the thing that falls into the center. Okay, yeah. Yeah, so can I talk a little bit more about how black holes radiate information? So this is something that I actually don't focus too much on my research. There's a lot of people that focus on the black hole information paradox, is what it's called. It's the idea that once things get into a black hole, information is destroyed because Hawking radiation is somehow completely thermal and it mixes up and scrambles all the information that can't be restored. So I don't know too much of that to be able to answer any question completely. I don't have the solution to the information paradox, for example. But that was the starting point, is that Hawking radiation somehow contains that information, but in a really highly scrambled way. And so in principle, you should be able to piece that back together. And there's some subtleties with that, but currently the problem is that people don't have a systematically perfect way of counting how much information actually exists within that radiation. So that's an active area of research. Maybe one of you will solve the problem someday. Okay, yeah. So I caught the first part of your question. You were saying, I guess when a black hole initially forms, there's a collapse that forms it. Then what was the?
Black hole as its mass. What role does the mass of black hole have to play?
Okay, so what role does mass play in its existence when it's decaying? Yeah, so basically a black hole only needs a very small amount of properties to characterize what it is. So for a Schwarzschild black hole, you really just need a mass. And that is the one number that you need that completely describes the entire space-time around it. And so when it starts to decay though, then the mass decreases. And that's basically all that you need. You can also talk about the spin is another way that you can characterize a black hole and its charge, or the three main quantities. So hopefully that kind of answered your question.
Essentially, black holes any star that has the same mass as.
Yes, yeah. So one thing that I didn't mention that I probably should have, if we were to then take this sun, for example, and collapse it down to a black hole, we would not notice anything different on Earth, except for that it would be nighttime. So a common misconception is that black holes suck, that they scoop in everything from around them like a cosmic vacuum cleaner. But this is not the case. All that we see is a mass. And if that mass is the mass of the sun, then we on Earth are going to continue to orbit around just like normal. It's not like suddenly we're going to be sucked in. So all that we see is the same mass. So that's an interesting thing. Okay, we'll take 2 more questions. So I saw your hand a while back.
You mentioned that the singularity, if I understand correctly, it's not a point, it's an infinite point. So is it just like infinite angular momentum that makes it into a plane, or how does it exist in 3 dimensions while being a plane?
Yeah, so that's a good question. So asking about singularity, how it makes sense that it's an infinite plane. I wonder if I have something here. Right, so I guess what you can imagine is that if you have some observer which is coming in and they fall in straight from the top and then go straight down to the singularity. And then you have another observer which comes in from, say, the side and they fall in straight toward the singularity. If we look at it from this view, we would say that both those observers are reaching the same point because they are both at the same radius in this coordinate system, but they are very causally disconnected from each other. And so one of them could not send a signal that would reach the other one because the space-time is falling faster than the speed of light. And so as it turns out, what that means is that these 2 observers would reach different causal points. And this sort of makes sense if we're looking at it visually because they would just end up on completely different points on this plane. And so part of it is just a visual effect that it looks all stretched out because of light travel time effects, but it's also causally, this is a surface and not a single point because every point on the surface is causally disconnected from the point directly next to it. So yeah, okay, 1 more question. Does anybody who hasn't asked a question? Did you have your hand back? Yeah. What was that last thing you said? Oh, so wouldn't those rays converge? They actually will not meet. So they will reach the same point within this coordinate system, I suppose. And so the singularity has a volume of 0 if you define a volume a specific way, but they are completely causally disconnected from each other, again, because of this thing where space is traveling faster than the speed of light. So it's a really weird thing that's going on there. If you were to add something like charge to the black hole that would push the space-time outward again and slow it down enough, then perhaps you could get the light rays to converge again if they slow back down to slower than the speed of light. But this is also something that is very problematic if you have a second horizon inside. And this is specifically something that I study, is how quantum mechanics makes everything blow up at this inner horizon if you do include it. So we don't want that to happen. And the result is no matter what, you're going to reach this space-like singularity. Okay, so I want to honor you guys' time since I know it's already 6:45. So I'm going to wrap things up here. I will stick around for however long if you guys want to come up and ask me any more questions. But thank you all for coming. If there's any pizza left over, feel free to get that. And thank you also everyone who joined on YouTube.